picking bigger numbers here on Machine Learning Basics. Hey everybody, Blake here. So this week I got a message from one of my viewers, a YouTube subscriber, who was working on a problem where on the surface it was a very simple, straightforward problem that should have trained up very quickly. But as they were talking about it, the training wasn't working. It wasn't converging. And they had described their scenario. And I had some things that said, well, you know, I might look at this and this and this. And then I came home and I couldn't help myself, and I, fired up Unity and basically wrote it up because the problem itself wasn't very hard, and I wasn't 100% certain why it wasn't converging. And there was a couple of things in there that I thought were a little odd. And so I said, you know what, I'm just going to try it and I'll make a video of it if I learn some interesting stuff. And we're here because I learned some interesting stuff and I was able to help this person. And now we're off in training and have a variety of potential solutions to this problem. But understanding why this one didn't work kind of out of the box, as it were, is actually a little bit of an eye-opener, and that's always fun when it's a simple problem that you can understand. So let me open up Paint, if I can type. All right, so here's the problem. You have an array, or list, whichever, of 5 items, right? And the problem, as stated, was, hey, go and pick out, if you have randomized numbers, find the 5. That's it. That's the problem. And then you get a reward if you get the 5, and you get nothing if you don't. That was the problem as it was stated. So one thing that struck me about that is, well, I don't know about this, if you find it, then you get a reward, otherwise you don't. In this case, because there's only 5 items, it's not that sparse. Like, you should be able to train on that and find it, and that shouldn't be a problem. But I know certainly for, very, very large spaces, sometimes you can end up where it's so sparse that you never observe the 5, or it ends up being kind of noise in the signal and it's not training. In this case, it should have been fine, and so it was a little odd that it wasn't finding the 5. There was also a timing issue, step size. He said, this game goes on for 5 seconds. And I said, that's really weird that it's going on for 5 seconds. I said, yeah, but it wasn't working when it was just one step. I said, you should be able to just do just one step and be able to do just a quick, here's the array, take a look at it, give me a response, and then grade it and move on with your life, on to the next scenario. And train and iterate really rapidly, and he had problems with that. I said, that's also really weird. I wonder what the deal with that is. And then the last thing that he mentioned that was interesting was he wanted this to be a continuous space problem, so that if he had, maybe 10 or 20 or 30 entries in this array, that it can go. And I look at this, I said, this is a very discrete space problem, and it seems to me that if we do this as a continuous space, maybe that's part of the problem, although that also didn't make sense because basically the approach was you go from -1, right? So if that's array index 0, 1, 2, 3, it's a terrible 3, and 4, right? Then you go -1 to 1, and then you normalize it basically, and you come up with your index value, and that's your choice, right? So you observe these, and then you choose an index, and if it's the 5, you get the reward. I said, well, that should I feel like that should work, but I mean, clearly it wasn't, right? As we were talking, this person had obviously tried. It's not like they were, doing something blatantly foolish or lazy. So they had tried a couple of things and they were going with it, and they had a problem with it. So I said, all right, I'm going to go. And sure enough, I had the same problems that they did. And we were able to get to the bottom of some of them. And one of them we were able to route around. We didn't really get to the bottom of it. But we're at least able to route around it. So it's nice because this is a very simple example. The code is very straightforward. It's much akin to when introducing arrays and randomization and things like that. We've written programs like this in many intro to programming courses, or when you go through tutorial series and you're learning a programming language. This is an array of size 5. This kind of scope of problem is the kind of thing that people are familiar with. So I said, all right, I'm going to take this on and take a look at it. The other thing that's interesting about it is we're in Unity. We're in this high-powered 3D game engine, and this is completely text-based. We don't have any visualization at all. So it's in the scene, main camera, directional light, doing literally nothing. Academy. In this case, I used the Ball 3D Academy. This Academy is... the reason I used it is it's blank, and so since it doesn't actually do anything, here it is. I just said, fine, I'll reuse that one less thing to code and worry about. So that just came right out of the examples in Unity. And I had to add a brain. And so you'll see here in my assets, I created a brain called PickBrain. Now, if I go to create, it actually goes off of my broadcast portion of my screen. But I promise you there's a drop-down list up here that says ML agents, and it says learning brain, player brain, or heuristic brain. So I selected learning brain because that's the learning ML agents learning brain. And so I click on that, and I said, all right, well, not copying any parameters. I wanted to do, this is the discrete version of my brain, right? And so the space size is 5. That's how many observations, right? Because we have 5 items in our array. And then we had one choice, and the branch one choice is from 0 to 4, which means that the size is 5. And so in the discrete space, it's going 0, 1, 2, 3, or 4, and it's picking the index directly. If we do the continuous space, right, then it's only one value, one action that's coming out, and we're clamping that -1 to 1, and then we're normalizing between -1 and 1, and that becomes our index, right? So we convert that into an index, and we use that. So, all right, that's fairly straightforward. So that's what our brain does. And then, so let's see, our academy, yep, and then we use that brain, and we give control of that brain off to the ML agent. So that's the one that's being used to learn. Max steps, we talked about max steps. I said, why don't we just set the max step to 1? That way, instead of waiting 5 seconds, you're going to iterate really, really quickly. And he said, oh, that didn't work. And so I tried it, and sure enough, it does not work with a max steps of 1. What will happen is it'll say, the first time it'll say the episode is complete, and then no other episode ever completes. And I don't know why that is, but it doesn't. And for some reason, the episode's never complete, and so nothing is ever learned. It doesn't converge. It basically doesn't do anything. So setting the max steps to 2 solved the problem. So instead of my value ranges being from 0 to 1, my value ranges are 0 to 2. So my maximum score is a 2 instead of a 1 because my max steps is 2. Because that works, whereas a max steps of 1 doesn't. I don't know why. I'm assuming it might just be kind of like some initialization order bug or something in there, and it wasn't important enough to go deep into. So that was one of the ones where like, yeah, we found it, we were at it around it. But it, yeah, not sure why 2 works and 1 doesn't. And then, so the game environment, again, so this is my new custom agent. We'll get into that in just a second. Again, max step is 2, and then reset undone is true. And the decision frequency is every step we want it to make a decision. So it has, for every game, it has 2 opportunities to pick numbers and maximize its score on a range of 0 to 2. So hopping into Visual Studio, this agent is pretty short. I could dump it in GitLab, or I could also probably just copy and paste it into the comments or description part of the YouTube page. That's how short we're talking. So in the scenario it was given, it was 1, 2, 3, 4, 5. Personally, when I can, I generally normalize from -1 to 1 or 0 to 1. And since these are reward functions, I opted to normalize from 0.2 to 1. So, I mean, if you multiply this by 5, then you get, the same problem, just 1, 2, 3, 4, 5. And so this is just kind of habit where I normalize. I don't think it really had any major impact. It would probably work fine if it was 1, 2, 3, 4, 5. So here are my values, right? I have a list of floats, and then 0.2, 0.4, 0.6, 0.8, and 1. And then I shuffle them, right? And the shuffle was just a quick shuffle routine. Nothing very special there. So then basically what happens, right, we've started up, which means that the game initializes, the agent looks, takes senses the environment, performs an observation, reacts to that observation, takes an action, and then receives or does not receive a reward based on the action, rinse and repeat over and over and over again. And so here we go. We, on our initialization and reset, we just reshuffle the numbers so that the numbers are always randomizing, and I did check, and that did seem pretty random. So collect observations. In this case, we're just reading the array to the ML agent, right? So here we go. For however many numbers you have, just read those off, and those are your observations. So in this case, we have 5 observations. And then the agent action, you'll notice that there are 3 versions of this. And so this was as I tested different portions of the approach that we discussed, and was honing in on what parts of this were or weren't working. And so we'll cover those. And then, the reset is just where we shuffle. And so the agent action, that's where things are interesting. So just to make sure that we're thorough here, okay, so the main camera, directional light, those are nothing. Academy just has the standard one. We have the brain, and that's the one we're learning from. And then the game environment, just has this pick agent, right? And then that uses the same brain. And that's it. That's all there is to our scenario. So in here, we have this first bit of logic was using the continuous space that we talked about, right? So -1 to 1. And actually, in this case, I didn't actually go to 1, because if I did a 1, that would be index 5. And so that was like 0.99999. That was the range, right? And so we took the action from the ML agent, and we clamped it to -1 to 5 nines. And then I added 1, right, which means that instead of, by adding 1, that means that instead of -1 to that, right, we remapped it so that that is a 0, and that is 1.999, right, and then we divide it by 2, right, and so that, once again, kind of gets us, the whole idea here is that we're getting ourselves back to this, 0 to 1-ish range, right? 0 to very close to 1. So by dividing it by 2, again, we're normalizing basically between 0 and 1, not inclusive. And then based on that, we multiply this number by the number of cells, right? So this becomes, this sufficiently small number becomes, still stays a 0, but then if it crosses 0.2, then it becomes a 1, and so on and so on, right? And so basically, we're going from 0 to 5, and so we're getting our indices from that, and then we see what index they chose, and then we pick their choice, and then we add that reward. So what's interesting about this, the original question was binary yes or no. Either you pick the highest value or you don't. If you pick the highest value, you get the reward. Otherwise, you get nothing. I said, well, I normally do more with gradients, and so I started with a gradient where the reward you pick is a reward you get, right? And so basically, you'll want to pick the 1, and you'll not want to pick the 0.2. But if you pick a 0.8, it's not the end of the world. And so letting it train on that. Now, we have gotten some okay results with that. And so this was actually, no, we did not get good results with that one. And so what happened with that one? Yes, here's the TensorFlow chart for it. We started, and you can see I restarted it once here and had some issues because I was learning the ML Agent 0.6 while I was doing this. We started at just under 1.18, and we ended up at the very last iteration at 1.21. So a whopping gain of 0.03, which. So this is, even though this looks like, oh, well, I can see a general upward trend as we're smoothing, I mean, this is like a 3% gain, 4% gain over the life of this. It might be better than that, but it's really abysmal, right? It didn't learn a whole heck of a lot as we were training it. And so I said, what the heck is going on? Why isn't it? I learned a tiny little bit, but it's in the noise. It doesn't really matter. And so that's when I added this one line about what index did I choose, and that helped me see what the problem was. So what's going on is that this is, instead of picking a linear distribution over floats, which kind of makes sense. You don't really want to do that because floats can get very, very large, or very, 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 very large positive or very, very large negative, with low precision. And so, those numbers aren't really helpful. Again, a lot of times when we do the ML agent stuff, we're constraining between -1 and 1. And so this started to make sense a little bit that maybe we have an issue in here. And so I just let it run and said, what indices are you picking? And so when I did the mapping with -1 to 1, and I was thinking, what are the raw numbers coming out of this vector action and what do they correspond to? What I found was very telling in that index 2 was being chosen a huge portion of the time. Absolutely huge. So I ran it until I got 50,000 index 2s. And then I said, well, how many index 3s did I have in that same time? And I'm not even going to draw that bar there because it wasn't even anywhere near that close. I think it was like 15 or 20,000 3. So this was at 50K. And if I recall correctly, I think this was more like 15, right? And then at 4, I think we were at like maybe 2 or 1.5, something like that. It wasn't much. And then we saw the same thing over here. And then I realized, oh, that is a belt curve. And index 2, right, that's going to resolve to the value 0. And then, that means that this is, around 0.5, right? And then, that's closer to 1, right? And that's negative 0.5. And this isn't quite right because those aren't the barriers. But, as you see, as you go further out and out, you get more standard deviations away, and you don't explore that space. And so what was going on is that even though these numbers were here, the algorithm was choosing the index in the middle far more than it was choosing any other index. So even though this was an extremely small state space, because of the way that we had framed this problem, presented this problem, and then taking and normalizing these inputs, we were getting just a huge bias in what index we were choosing, and therefore it would almost always choose index 2, and so the results it was getting as a reward were basically random noise. So that's why this continuous approach didn't work for this case. So I said, all right, well, we know that doesn't work, and at least now we have a better picture as to why, and that, eventually it probably would work, right? But there's this, again, a huge bias. There's a problem here. And you could try to rescale and do this, but ultimately this problem is a discrete problem, right? It goes, you have 5 possible values. That's all there is to it. And so let's try this as a discrete problem instead. And so the code to do that, in this case, again, I was sticking with kind of the gradient thing where I went 0.2, 0.4, 0.6, 0.8, and 1, and what you picked is what you got. And right, so if you observe this array and then you pick the one that said 0.6, that was your reward. And so the logic on that is really, really freaking simple. It's 2 lines of code. I only have this choice variable in here so that I could Debug.Log it out, because otherwise it would be 1 line of code. So that was really straightforward. And so the question was, well, how did that train? And I believe that is not that one. That was another early one. So I guess it's going to be the gray one. Yes. How did that train? Well, that trained pretty good all of a sudden. No, I think that green one was right. So at first I did a quick test, and I was severely underwhelmed by it, but I said, you know what, I'm just going to let it run longer and maybe get more lucky. And that's pretty much what happened, right? And if you compare the two, this was just a bad run. Like, it did okay in here, and then it tapered off for some reason. But then the next run with discrete, it learned a lot, right? So all of a sudden, instead of being in this 1.2 range, right, in 200,000 iterations, it ended at 1.7. And so that's actually a pretty decent score. It's far from perfect, and, this is like, I feel like we should be able to get this perfect. But at least it was reasonable. I said, okay, well, that's educational. And then when I watched it play, the other thing that was interesting about it is because it was an imperfect player, and because we had these weights, the choices that it would make reflected these weights. So how frequently it would choose these. So it would choose 1 the most often, and then after that it would choose 8, and then it would choose 6 less frequently, and 4 less frequently, and 2 0.2 very infrequently, right? And so it actually kind of reflected the frequency of its choice was a reflection of the value of that item. And so that was actually really interesting, because sometimes when we're doing this kind of stuff, we don't want to make a perfect player, right? If we're playing an opponent to a human, right, we want our game to be fun, not necessarily to be perfect. And so to have it where this would mostly choose really good things and then very occasionally just make a really crappy mistake, that was actually a pretty interesting space to be in, because then you had an opponent who would probably be fairly challenging, but wouldn't automatically crush you with perfect knowledge that machines often do when you're playing against really, really strong AI. So I thought that was interesting, that was a kind of a good space to stop at, where the reward was good but not awesome, and that, some of these choices were, a 0.8 isn't a terrible choice. It's not as good as a 1, but it's certainly way better than a 0.2. And that its actions reflected that. And to be honest, when we're talking about a perfect player in a perfect game, even a human is sometimes going to press the wrong key, and it would be hard for a human to even be a perfect player. And if they accidentally press the wrong key, right, it might be the 0.2 instead of the one that they meant. And so, having an absolute perfect player is sometimes very detrimental, because humans, just to the nature of human error, can't beat them. But at the same time, I felt like, okay, so this is an interesting state. but I also kind of want to crush this problem and come up with a perfect player, right? So I said, you know what, this worked, and I don't think we're done, and I'm going to go to bed, so I'm going to let this puppy run. And so I just let it run for 2 million iterations, and sure enough, here we go, right? Again, the maximum score is 2 because there are 2 steps. And so how close did we get? Well, we got 1.995 out of 2. So that's a pretty darn good player. And we didn't even have to run it for 2 million. I'm going to just let it run overnight. But, you know, at 1 million, it was at 1.993. You know, at 500,000 steps, you know, 500,000, it was at 1.975-ish. So, you know, clearly you didn't have to run it this long, but, you know, this trained very, very quickly because it's only 2 steps. And you know, and the internal logic here is so fast. It trains very quickly. Said, you know, yeah, just do your thing. Keep going. And so, but yeah, didn't need to train it that long. But I love this beautiful asymptotic curve. Like, this is the kind of thing that makes mathematicians smile. And it shows that we're absolutely converging on a maximum value case here, and so that is about as pretty a training curve as you are going to get, especially since it is stretched over a long enough area that, you know, you can pause it at any point in here and have, you know, kind of a poor player, a decent player, a good player, an absolute, you know, unbeatable player at various stages of this training, which I thought was interesting. So I said, all right, the original question, though, was kind of this binary yes, no. If you pick the highest value, the 1, then you get a reward of 1. Otherwise, you get nothing, right? And I said, what happens if we do that training instead? Because, you know, we certainly got this to train, but is this training as fast as it could? Or was that also part of the problem, that it wasn't searching that space properly? And, you know, we learned through the continuous space, it wasn't searching that space properly. It was biased towards one of the indices far more than the other ones, but was there something else going on? So I said, all right, let's go ahead and code up this Boolean reward where we say, okay, we have a vector action of 0. That's the choice. So we're still in discrete space, and you just, this is your choice. And if you chose 1, then you get a reward of 1. Otherwise, your reward is nothing. And you add that. And I said, all right, how quickly did that train, and what did that do? Yeah, I stopped it because there was no more point in going on. It absolutely sailed through the training. And what's interesting is you can see where it learned stuff, right? It has this neat little step function going on where it was like, oh, yep, learn something, learn something else, learn something else, learn something else, you know. And it's going through, and then it as flat as can be. This is absolute pancake. You know, this is value 2 basically completely across. There's, I guess, a couple of minor outliers in here, but it's basically as flat as you can be, right? So in under 150,000 steps, you basically have a perfect player that can play it every time. So long as your problem domain is small enough that it is able to explore that space and find the best possible value, then it likely will, and that will dominate the training and happen very, very quickly. And so that really worked. Now, what's interesting about this, though, is if you have a player that has this, right, they will almost certainly pick, you know, if it's over here, they will always pick the right answer every time. Over here, they will almost always pick the right answer, but if they don't pick the optimal answer, it is completely random what non-optimal answer they're going to pick, because even though these numbers are closer, the reward is the same, and so these are, as far as choice quality are concerned, indistinguishable from one another. So there is no, oh, this is better than that, or that's better than that. Like, if you pick one, then that's it. But otherwise, it could be any one of these, which is kind of random as to what it picks. So that is going to play very differently. So if you look at these two curves, something trained in here is going to play very differently than something that's chosen in here. Even though they overall might have the same score, they're actually going to have probably a different feel when you play for it. But again, this hit the training. Like if you wanted a perfect answer and just wanted to get that, then that was absolutely a great way to go, because it just got rid of all of that noise and all of the increments and just said, boom, here it is, here's the answer. And yeah, again, that trained super quick. So there it is. That is the 3 revisions of the agent action and reward logic that I have. The observations pretty much stayed the same the whole time. Yeah, and then resetting and shuffling, that stayed the same the whole time. So this was just 3 different ways of framing the problem and 3 different ways of looking at rewards, and understanding kind of the intricacies of some of those behaviors and what that meant when we trained it up and got a result. I thought it was actually very interesting. So many thanks to this viewer for bringing this up and mentioning this problem, and I'm glad we were able to work this through. Their next thing was, okay, I want to make this so that I have any number of items in my array and generalize it to different array lengths. And they were able to come up with an encoding. Now that this was up and running and it was training, they were able to find a way to do that. Now, I don't know if that means that you're just training on a maximum number, and then, if you just say, okay, up to 100, an array size of 100, and then anything smaller than that would be fine, because I don't think it'll generalize. If you train, up to an array size of 100, I don't think it'll generalize and say, all right, now I have 150, I'm not sure it'll know what to do with between 100 and 150, but it'll still do fine between 0 and 100. I'm not sure. My intuition is it wouldn't generalize and work that way, but if somebody has had good luck with that, I would certainly love to be wrong and learn more about how well these generalize into those kinds of scenarios. As usual, if you feel like you've gotten something out of this video, hit that like button. If you've gotten something out of a couple of my videos, then considering hitting that subscribe button. Or if it's been super helpful to you, consider Patreon. I am very grateful to my Patreons, my patrons, and the individuals who also occasionally just give me one-time donations instead of becoming patrons. All of that is hugely motivating for me. And so I do appreciate it. And at some point, I hope to find ways to either improve the quality of the production of these videos, or if, in time, I don't know of good ways to do that with, just buying better equipment, better camera and whatnot. Then I also hope to be able to potentially hire artists to create open source art assets, because personally I feel that as an indie, as a programmer indie who has like games that they want to create and things that they want to explore, having quality art is a great way to get some of the work noticed without just it being gray boxes. And it also feels good to have quality art and attractive things, even though I'm not an artist. And so I would love to be able to hire an artist and say, hey, go ahead and, make us some open source rocket art, and that anybody can use these rockets or spaceships or whatever it is for their personal projects, so that as they're learning, as they're growing, that they're able to use quality assets that they don't have to invest huge amounts of money in. It's something that I personally think would be very liberating as more of a coder side of the creative process. So that's kind of where I'm hoping to go with that down the road as we get there. So anyway, thank you for watching. Thank you for your questions. Feel free to leave questions here on YouTube or on Patreon if you're a patron. And I wish you good luck and happy learning. Take care.